Okay, let's get started. I was telling you about superconductivity. I want to finish that up today and then move to the last subject we'll cover this semester, which is mechanical properties. The important thing to remember about superconductors is that they represent a new phase of matter and a new kind of behavior. A superconductor is not just a good conductor. A good conductor conducts by means of electrons, they're fermions, and there's no way to get current in a conductor that conducts by means of fermions without some resistance. Superconductivity is based on creating current carriers that are not fermions but bosons. And the simple way to do that is to get the electrons to pair together in what are called Cooper pairs. If two electrons pair together, their spin is not 1/2, but either 1 or 0. And as a consequence, they are not fermions, but bosons. As soon as you have a group of bosons, like phonons, then you can put as many particles you want in the lowest energy state. And if anything happens, they try to conduct electricity, they get scattered into some high energy state, they'll immediately drop back into the low energy state again. So as a consequence, you can conduct current with 0 resistance, provided you do it by means of these so-called Cooper pairs. The superconducting elements in the periodic table are shown here. Of course, ferromagnetic elements cannot be superconducting. I should have mentioned that briefly. There are two properties of a superconductor, really, and they're tied in together. Superconductors have 0 resistance, strictly 0 resistance, not approximately 0. The resistance of a superconductor has been measured with great precision and is lower than any number that one can measure. They also exhibit what's called the Meissner effect, that is, that they exclude magnetic fields, and that can also be tied in with the 0 resistance. Because if we put a material in a magnetic field, the diamagnetic behavior says that you will introduce a circulating current that opposes the field. If there's no resistance, that circulating current can become as big as it needs to be to exclude the field, and that's what happens. That's the Meissner effect. Superconductivity exists near the origin of coordinates in a 3-parameter space. To have superconductivity, the temperature has to be below some critical temperature Tc. This is necessarily true so that these weakly interacting Cooper pairs will remain intact. The magnetic field has to be below some critical field h sub c, and the current has to be below some value Jc. So it's in this little quadrant down here near the origin of coordinates in this 3-dimension system that we find superconductivity. There are two kinds of superconductors. Let me just say that superconductivity was discovered at the end of the 19th century. I think I told you the story last time. It was virtually useless, except as a scientific curiosity, until sometime in the 1950s. And the reason is that the superconductors that were known at that time were superconductors which are called type 1. In a type 1 superconductor, if we raise the magnetic field of the superconductor, then the material can remain superconducting. As we raise the magnetic field by the Meissner effect, we have a magnetization within the material that's exactly equal and opposite to the magnetic field. That situation persists until the magnetic field hits a critical value, which is Hc, at which point in a type 1 superconductor, the field penetrates the material completely and superconductivity is immediately lost. Since this critical field is always a relatively small number, and since the critical current that a superconductor can carry is rather intimately connected to the critical field, a circulating current produces a magnetic field, these type 1 superconductors are relatively useless for the purpose of carrying current. There's certain applications you can use for them, but when it comes to making a device that needs current, such as a power unit of some sort, the easiest thing is just a solenoid magnet, where you wrap the solenoid with a conducting wire to create a magnetic field. They're relatively useless. Until about the 1950s, this was the situation. Superconductivity was a scientific curiosity. Along about the 1950s, late 1950s in particular, it was discovered that there's another type of superconductor, which is called a type 2 superconductor. Now, in a type 2 superconductor, when we increase the magnetic field, the magnetization increases, but before we get to the critical field, we begin to get slight penetration of the magnetic field into the material. But that penetration is only partial. And what happens is that the magnetization within the material drops below the applied field and begins to gradually drop off, so that we get partial penetration of the magnetic field, not complete penetration. And penetration is not complete until we get to a much, often orders of magnitude higher field, which is called the upper critical field Hc2. And the fact that we can get, because superconductivity means 0 resistance, if you have a wire that is even partially superconducting in its cross-section, it will exhibit superconducting behavior, and you can pass a superconducting current through it. So we can get superconductivity all the way up to this upper critical field Hc2, and it suddenly became possible to make useful superconductors, things that could actually carry current, and you could, for example, make windings out of. All of this happened about the time I was here in college. So I'll tell you a story about superconductivity that doesn't reflect very well on me, but it does have a message I'll get to in a moment about material science. When I was a freshman in college, I took what was MIT's equivalent of E45 and was offered a summer job by Professor John Wolf, who taught that course. So I go into it, and he was working on the first type 2 superconductors. The first really useful-looking type 2 superconductor was the element niobium. Most elements are type 1 superconductors. Niobium was type 2. And people had discovered that if you took niobium, you could get it to carry a decent critical current. And if you deformed it by drawing it into a wire, for example, the critical current would go up. So John Wolf had the, turns out, really clever idea that if he could take niobium and get the dislocation density to extremely high values, that he might get an even better critical current. So he came up with the idea of taking a niobium tube. The highest dislocation densities you can get into a material usually are by machining it and just taking the shavings. You know, if you use a cutting tool and you start machining the material, little shavings come off. They're very heavily deformed and have very high dislocation densities. So he says, what I'm going to do is just machine a bunch of niobium and create a whole pile of shavings, pack the shavings into a hollow tube, draw the tube down into a wire, and then have real good properties. So I got the tedious assignment of picking up all these little shavings and packing them in the tube and putting plugs on the end and drawing them down. Now this was being done in an old foundry, not a clean room. You know, there's dirt all over the place and goop on the floor and cutting oils everywhere and everything. Something in there. Everything worked fine until I started to draw the wire down. And I hadn't gotten the plug quite in all the way, and the plug popped out, and all the shavings spewed all over the laboratory. They're all over the floor. Now, if I'd been an honest person, I would have immediately gone to Professor Wolf and said, uh-oh, I really screwed up. I messed up my last month's work. I was not honest. And what I did, I was scared to death of the guy, to be honest about it. He was a pretty formidable character. So what I did was I went down on the floor, I gathered up all the pieces with all the crud that was around them, packed them into the tube, and drew it down. Well, the stuff didn't get tested until quite a while after my summer job was over. So I ran into Professor Wolf and very tentatively asked him how things had come out, expecting him to say, that piece of crap you made, I'm going to never get a recommendation from me. And he says, you know, we tested a whole bunch of wires, and the only one that really had exceptional properties was the one that you made. And he said, I've got a couple of graduate students trying to reproduce that now. Well, one of these guys told me later they never really were quite able to reproduce the properties they'd gotten in my sample. No way was I going to tell them what really happened. They didn't ask. Let me tell you why that worked. And actually, my unfortunate experiment worked for precisely the same reason, or very nearly the same reason, that all the people who tried to make high TC superconductors work as current carriers were not really able to do so in the effective way, even though there were thousands of physicists and billions of dollars spent on it. So what happens? What's the metallurgy of this? If you look at the type 2 superconductor, and I go into some of the physics of this in the notes, I won't try to do it here in class. What actually happens when you start getting penetration into a superconductor? The field doesn't penetrate completely. It penetrates in certain quantized vortices, which are, if you want, little tubes that have a one quantum of magnetic flux associated with them. And these tubes do not fill the whole material. So if you beef up the magnetic field, starting out at the lower critical field, you start getting the first tubes in. As you beef up the magnetic field, the density of these tubes increases and increases until finally at the upper critical field, the whole thing is populated with these quantum vortices or tubes. Now suppose I take this type 2 superconductor and I now attempt to pass a current through it, which is going to, by the Lorentz force, put a force on these magnetic vertices. Now if this is a perfect material, as soon as I start trying to put a current through it, the Lorentz force starts pushing on these magnetic vertices, and they start moving through the material. Well, just the friction of them moving through the material is going to heat up the material, and superconductivity is going to be immediately lost. So ironically, superconductivity is the opposite of ordinary conductivity. If I want copper to be a good conductor, I need it to be very clean. If I make a superconductor that's very clean, that's a disaster, because there's nothing to keep these vortices inside the material. They get swept out, and I can't carry any current. If, on the other hand, I put all kinds of dirt into this material, then there are all sorts of microstructural obstacles down here that get in the way of these vortices. They interact with the vortices. They resist their motion. They make it difficult for these vortices to move, and therefore the material can carry current. So with a superconductor, granted, putting it well off the floor is not the best solution to this. There are much more sophisticated ways to do it that we know now. But to make a good superconductor, one that carries a lot of current, you don't want a clean material. You want a dirty material. You want to dirty it up in intentional ways, so you pin these vortices, make it very difficult for them to move, and in that way create a material that can carry current. And well, for example, one of the best type 2 superconductors now is niobium-310, which is widely used, and it has a critical current characteristic something like this, provided that it is made, as I'll show you in just a minute, in a way that provides lots of pinning sites for these vortices. Oh, good God, no. I think I told the story for the first time a couple years ago. I do not recommend that. But since it's Good Friday, I've got to be honest. It was simple. But it worked, and for that reason. And had we put 2 and 2 together, people would have said, hey, wow, I see why it worked. But that wasn't done at the time. I'll show you how we do it now. Here, incidentally, are just some good type 2 superconductors. All of these materials, the good type 2 superconductors, have the problem that because you want material, because your Cooper pairs are coupling electrons to vibrations, you want materials that are almost unstable, that have big whomping vibrations. That means you're dealing with materials that are almost unstable. You then want to make them dirty. So good superconductors are lousy materials. And they're good superconductors because they're lousy materials. But that makes it enormously challenging to make them into wires that you might use in a practical way for various applications. Among the best, the thing that is still used, for example, for most accelerator magnets, and there's a big program up at LBL on accelerator magnets, uses niobium tie, about 50-50. Niobium titanium alloy is just an alloy. And it has the advantage, even though the properties aren't super great, a TC of 12 Tesla, a K, a HC2 of 12 Tesla, you can work this stuff. It's a ductile metal. And therefore, whenever you are making magnets that you want to sell, superconducting magnets you want to sell for prices that ordinary human beings can afford, they're almost always made out of niobium tie. The magnets they use for MRI treatments and such things, accelerator magnets and most accelerators are niobium tie. As we go up, we get to the A15 compounds, niobium-310, niobium-3 germanium, which are kind of the workhorses of the really high field magnet business. What are used for, are being developed for the fusion program, they're used for high field magnet separation, other high field applications. They have critical temperatures 18 to 20 and critical fields of 24 to 38 Tesla, somewhere in that region. Niobium-310 is the most widely used of these because we can manufacture it in a convenient way, as I'll speak in just a moment. Lead molysulfide I don't think has any applications. The oxide superconductors, yttrium, barium, copper oxide, the bismuth, strontium, have critical temperatures above 77 Kelvin and huge critical fields at low temperatures. So when these came in 1987 was the critical year, everybody just went berserk. The physics community said, wow, we're going to revolutionize engineering as of tomorrow. And I urge you to go back and look at Scientific American of that year, some of the newspapers, and see the stories. Never happened, of course. The reason it never happened is very nearly the same, and some of us saw it at the time. We were the deniers against the scientific consensus, and we kind of dumped on them. But it was kind of obvious why they were going to have trouble making these things work. The big advantage in these would be, of course, if you could get superconductivity up around above 77 Kelvin, so you could cool your magnets with liquid nitrogen instead of liquid helium. Liquid nitrogen is relatively inexpensive. It's all over campus. Liquid helium is costly, and it's limited in supply. Why couldn't you do that? You can't do that for the following simple reason. If you go back and look at what you need to do, you've got to use the microstructure of the material to pin these vortices, to keep them from moving. But pinning things like this, at absolute zero, all you've got to do to pin something is to put in something that has a strong interaction with it. But as temperature goes up, you've got to worry not just about the energetics of the interaction, but about the thermal fluctuations that you have in the system. And what happens with these superconductors, as you might imagine, is that as we get to a decent field and a decent temperature, and this is kind of a typical plot for an oxide superconductor, all of a sudden you get what's called a vortex fluid. It becomes possible when you put in microstructural barriers for these flux lines to liberate themselves by thermal activation, basically the same thing that causes high temperature creep in a dislocated material, which we'll talk about later. And so they're able to move. And so you can't get the critical current up very high. And this is the battle that people have been fighting ever since 1987, and no one has really made that much progress in beating it. The one thing that you do use these kinds of materials, they're used in Josephson junction devices that unfortunately I don't have time to talk about. These are used in what we call SQUIDs, superconducting quantum interference devices that measure very accurately magnetic fields. SQUIDs are, for example, used to measure brain waves and try to see what you're thinking. There are physicists out there who say they can tell what you're thinking by measuring the waves coming out of your brain. I hope they're wrong, but maybe they aren't. But the other application for them, this very high critical field means that if you want to make a magnet that has a huge field, you need a superconductor down at the core where that field operates that has a very high critical field. So you find these oxide superconductors being used in the cores of very high field magnets, 30, 40 Tesla magnets, to take advantage of this big high critical field down at 4 degrees Kelvin. And of course down there you don't have to worry about thermal activation, so you can get decent currents through those superconductors. But that's basically what happens. Yep. Well, I can go into what I think. You know, the jury to a certain extent is still out on what the exact mechanism of these oxide conductors is. For example, it's still a matter of some controversy whether the things carrying current are Cooper pairs, electrons, or whether they're hole pairs. So there are a lot of questions still to be answered about these. From a scientific point of view, these are very fascinating materials, but they have not had the engineering potential that the people who first discovered them thought that they would have. It will come. Over time, people will find more and more applications for these higher temperature superconductors. It's happening. Squids, for example, and such things. But I think it's true in general. If you see a headline in the newspaper saying such and such a material has just been invented, the world is going to change, sell the stock of whatever company is doing that short immediately, because it just doesn't happen that way. But even the transistor, you know, we had transistors in '48. The first real commercial application was the transistor radio out of Sony in the late '50s. It's just the way things happen. Engineering does not move instantly. It moves at a surprisingly rapid rate these days, but it doesn't move instantly, and you have to take that into account. Let me talk about the niobium-310, which is kind of the workhorse high-temperature superconductor. The reason niobium-310, again, manufacturing is a huge issue. Now, what you can do with niobium-310 that makes it manufacturable is that niobium is, of course, a metal, and you can draw niobium wires down very easily. It's quite ductile. Niobium-310 is as brittle as can be, cracks with no problem at all. But what you can do is you can take niobium wires and encase them in bronze, copper tin, then draw them down into a very fine filament, and then heat the filament up so that it extracts the tin from the bronze and forms niobium-310. And the way you do that, because you want something that really does a good job of pinning these vertices, you want very, very tiny wires, and you want the wires to be internally defective. So we take, basically what you do is you take a bronze blank, fill it with copper rods, draw it down into a wire, take a whole bunch of those wires, bundle them, draw that down into a wire, take a whole bunch of those, bundle them, draw that down into a wire, until you get something that looks like this, where you have all these niobium wires sitting in this cable, sealed off with some sort of tantalum barrier or something of the sort. Now you heat them up. Heating them up, you get the niobium to react with the tin, and here's a typical niobium-310 filament. There's still a tiny bit of niobium left in the core. This is a very, very fine-grained niobium-310 on the outside. In fact, we will often add things like magnesium and such things to keep these things fine-grained. And so you end up with many tiny filaments, all of which are very fine grains, and by doing that, you create a very defective material, effective in pinning vortices, and it has a good critical current. And this is kind of the workhorse superconducting wire for the very high field magnets. Ordinary magnets still use niobium tie. If you're working on a magnet with a operating field less than about 5 Tesla, you go with niobium tie because it's cheaper and easier to manufacture. But that's about all I have time to say on superconductors. Fascinating area. But the engineering importance really hasn't hit. Maybe it will one day, who knows, but it hasn't yet. We'll now move to the final subject in this survey of material science, which is my area, which is mechanical properties. And in mechanical properties, we'll really talk about three things. Elastic deformation, materials that deform elastically and recover their shapes. Plastic deformation, where we load materials so that they undergo a permanent change in shape. And finally, fracture, how things break. The mechanical properties of materials, in fact, you'll see this in a lab. The usual way to measure mechanical properties for engineering purposes, the thing that gives you the values that you see tabulated in handbooks and that civil and mechanical engineers design to and so on, most of them come out of just a normal tension test. In a tension test, you take, well, a cylindrical bar or sometimes a sheet sample. You put it in a machine that pulls it, and you measure the change of length of the sample as a function of the load P. You'll see that, I don't think you have yet, but you'll see it in the laboratory. We'll put in a sample, we'll pull on it. As the load increases, the sample stretches out. And the typical curve on that will look something like shown at left here, where you have a linear region that started off. This is for a typical ductile metal. It then loses its linearity, it then peaks out, drops off, and finally fractures out here at the far end. In this test, of course, you are, in a sense, you're not really measuring material properties, because this test is measuring the geometry as well as the materials. You know, just from a rubber band. A thick rubber band is going to take more force to stretch than a thin rubber band. So you've got to do something to get the geometry out of the problem. And to do that, we recognize that the relevant load is the load per cross-sectional area. So you define the engineering stress as a load divided by the original cross-sectional area. The engineering strain is the change in length divided by the change in length, and that turns this curve into a stress-strain curve, in which we plotted the engineering stress versus the engineering strain. These are the curves that you will see in engineering handbooks, and they give rise to the data that you will read out of engineering handbooks. There are, in fact, a number of parameters that are, well, to begin with, this engineering stress-strain curve lets you easily identify three regions, three types of behavior you find in typical ductile materials. Down here where the strain and stress are very low, you get elastic behavior. And in a typical metal, the curve will be linear over that region. You will then begin to deform the material, a permanent change in shape. That's plastic deformation. The curve will bend over and will increase in strength as you continue to deform it. That's a phenomenon known as work hardening. However, as you continue to deform the material, the stress will eventually peak out. That's what's called the ultimate tensile stress. Where we start plastic deformation is called the yield stress. And here we begin to get plastic instability. That is, the deformation concentrates in what we call the neck, and then the material fractures. Well, let me go back. From this test, we get a whole bunch of properties that you'll see tabulated. The elastic modulus is simply the slope of the initial portion of the stress-strain curve. That tells you the proportionality between stress and strain. The yield strength is a measure of where the material begins to sustain plastic deformation.